Hello, in this video we are going to look at the directing effect of the electron donating groups in an electrophilic aromatic substitution. Okay, so the electron donating groups, they activate the ring, so we do actually call them ring activators because they make the ring more nucleophilic so that an electrophilic aromatic substitution can occur easily. Okay, we're also going to look at the electron withdrawing groups. So in an electrophilic aromatic substitution, these groups actually withdraw the electrons from the ring, making it less nucleophilic. So they make it less deactivated. We're also going to look at their directing effect on the ring, whether or why they have to direct the incoming group to the meta position. So except with the use of halogens, which actually direct the incoming group to the ortho para position. Now let us start with the ring activators. So assuming we have an aromatic compound like anisole, that is the methoxy group as a substituent. So the incoming group will either be installed in the ortho, in the meta, or in the para position. When we draw the sigma complexes, for the first one, of course, we're going to have the three common sigma complexes, the ones that we have been drawing in our mechanisms in the previous video. Now, we can draw those three complexes, but when we have the incoming group installed in the ortho or para position for an electron donating group, then the electron donating group can actually lead to an extra stabilization by donating electrons to the ring. Okay, so it utilizes the two lone pairs on the oxygen to donate. It uses one of those lone pairs to donate an electron, which leads to extra stabilization. Okay. Now, if we have it in the meta position, that does not occur because it bypasses the place where the charge could be stabilized. Okay? So if you try to utilize an electron to stabilize the charge, there's no way that would happen. It would bypass the other position. So that goes there. This one is going to go there. And there's no way it's going to stabilize that. So therefore, it's only the para and the ortho positions that have extra stabilization. But when you look at the ortho and the para, which one is going to be more favored? Well, by looking at the para position, you can see that there is less steric effect. There is some crowding in the ortho position. That crowding leads to steric effect. That steric effect now makes this compound at least unstable when compared to the one in the para position. So ring activators direct the incoming group mostly to the para position, which is the major product, except for toluene, where of course toluene is just kind of a methyl group. It's affected by other factors, including solvents, but it forms mixtures almost 50-50 for the orthopara, but the major product tends to be in the ortho position, probably due to the smaller size. Now let us look at the ring deactivators. Now here again, let us look at the three cases. If we have the incoming group installed in the ortho, meta, or para positions, then what really happens? So we're going to draw the three sigma complexes. There is no extra stabilization, okay? But within the three sigma complexes, it happens that the ones in the ortho and the para positions two of them, okay? So one of the ones in the para and one of the ones in the ortho positions are not actually stable resonance structures, because we have the nitro group, which is an electron withdrawing group. So the nitrogen is actually having a, now look at it this way. We have R, nitrogen, the nitro group is like this. That's the nitro group, okay? So we have the nitro group with a positive charge, and you're placing another positive charge here. It's not going to be happy. So that kind of interaction is not favorable. So when you have one of the resonance structures in the sigma complex having a positive charge next to an electron withdrawing group, then that resonance structure is not stable. So then we end up with the one in the meta position being the most, the three of them are more stable, so the meta position is favored. What about the halogens? What happens? Well, halogens are deactivators. They deactivate the ring by induction because they are electronegative. So they can deactivate the ring by induction. But they also activate the ring by resonance. Okay? So what happens is that in the process of the reaction, these two factors are competing. The induction effect, and then there's the resonance, which leads to extra stabilization. Okay? So the directing effect is controlled by resonance due to the extra stabilization. But induction actually prevails, so we end up calling them ring deactivators, except that they will direct the incoming group to the ortho para position due to extra stabilization. Okay? And in this case, just like the other activators, they will direct the incoming group to the para position being the major product and the ortho position being the minor product. And of course, the halogens have larger atomic size, so that reduces the steric effect that would be experienced in the ortho position. So let's assume we are doing nitration and you have your starting material. How do you predict the product? Well, we do have the methoxy group, which is activating. Then we have the aldehyde group here. So we know that is deactivating. So the directing effect is going to be influenced by the more activating group. So because the para position is already occupied, so the methoxy group is going to direct the incoming group to the ortho position. Okay? So the more reactive one, or the one that is more activating, is going to influence where the incoming group is going to be installed. But it also happens that the electron withdrawing group prefers to have the incoming group installed in the meta position. So this is ortho for the electron withdrawing group. This is meta. So in other words, both of them are happy because they have directed the incoming group to the right position. What if we have two electron donating groups? Okay, so here we do have the methoxy group and we have the methyl group. We know that the methoxy group is more activating. So therefore, the incoming group is going to be ortho to the more activating group. So the methyl group here is not going to have any influence in the presence of a stronger activating group. What about if we have like the isopropyl group and the methyl group? Okay, so what's going to happen? Let us see what happens. And we do have them kind of, one of them is in the meta position of the other. So let us see what they are going to do in the process of nitration. Where is the nitro group going to be installed? Now, the one that is directing to the para position is the isopropyl. It's going to direct the incoming group to the para position to avoid steric effect. But we know that the methyl group also wants to direct the incoming group to the ortho position. So then it's going to be happy. But what if it wanted to direct it to this ortho position? So we might end up with this kind of structure. That's not going to happen due to steric strain. So this is not observed, though it is one of the likely compounds, but it's not going to be observed. So the products that are formed is where the minor product is the more activating group directs it to the ortho position, and it's going to be para to the methyl group, which is still okay, but then the major one is where all of them are happy because each of them feels like they have directed the incoming group to where they want it to be. Let us look at an example of how to do some synthesis involving these compounds. So assuming we want to synthesize this product, and obviously this group is activating the tert butyl. So it's going to install the incoming group to the para position. But we want it to go to the ortho position. How do we do that? Well, we can utilize the sulfonation desulfonation as a protecting and deprotecting group. So we can install the sulfonate in the ortho, well, in the para position. So that means this position is not going to be available for any substituent to be directed. And then once we install that, then we do bromination to have bromine going to the ortho position, and then we can do desulfonation using dilute sulfuric acid, and we end up with a product. Okay? And that brings us to the end of directing effects. There's a lot of other practice available in the book. Make sure you go over them. Thank you and have a good one.